So, next part of the lecture will be on gravity structures. Now, the basic thing that we have done in our structural analysis, why we are going for these two types of structures. So, the first structure that I have described is that is basically your pile foundation. So, this was what we were resisting, that was the overturning moment. So, stability against overturning is the prime consideration for the stability of the structure. So, in any case, in offshore foundation you have to resist the overturning moment. So, this is very crucial. Now, how you resist that, that is your problem, isn't it? So, that you have to decide. So, that decides on the type of structure, that is, or type of fixed structures that is normally designed. So, basic load that is coming is, what is your load? Load is your overturning moment. And the structure actually normally resists this load. So, this is the external load that is coming onto this structure. Now, jackets, the pile actually is resisting the moment, and that is why I have told you in the jacket, the pile, there is a tendency to bend. In the pile, if there is a horizontal load coming right at the sea level, the pile will no more be straight like this, but it will start bending or flexing. So, that is why the problems that we are having with this is you should have laterally loaded piles. So, laterally loaded piles will have inherent capacity of resisting, this is called pile flexure. So, bending is the analysis which we take recourse to when you are designing offshore piles. Now, what about these gravity structures? Now, these type of structures, again the same overturning moment is coming here. Now, one thing you should note, that gravity structures and the jackets, they are normally in shallow water. Say gravity structures. Now, here I am not writing pile because I have written that. So, these are normally located in shallow waters. So, shallow water, you first calculate the load. Now, this load you calculate from what? From shallow water wave theory. So, this is where your hydrodynamics is going to come. So, shallow water wave theory, you employ all your shallow water formulas. Normally, in shallow water, they employ what is the linear wave theory. The linear wave theory you can use, but for shallow water. Followed. Now, these gravity structures are normally located in shallow water, and here you will find now why you go for gravity structure. Gravity structures are more costlier than pile structures, but because of soil characteristics, soil or seabed characteristics. Now, what are the seabed characteristics? Soil seabed characteristics where pile driving is not feasible. So, pile driving is not feasible where, in what region? In rocky soil strata. Rocky soils. Your soil is made up of rocks. There the pile is going to, not feasible means pile will bend. While driving. So, this is phenomena that is going to occur. So, here you cannot drive piles, but for gravity structure, one thing you should note that the soil should have good bearing capacity. Because your gravity structure is having large weight. Say gravity structure weight will be of the order of gravity structure large weight. Say 2,40,000 tons. So, this is a typical weight of a gravity platform. So, in order to resist this load such that your structure does not go down into the soil, that is, the soil should have, the bearing capacity of the soil should be good. Now, soil basically you will find there is a bearing strength and there is a shear strength. Soil actually is marked by two characteristics. One is called the bearing strength. So, this in soil mechanics you will come across. This is called a bearing strength and the other is called a shear strength. These are two types of soil that you will come across, bearing strength and shear strength. Now, if there is no shear strength, then that is called a no shear strength. I think this particular type of soil is called cohesionless soil. So, example is sand. Sand is not cohesive. You cannot take it in your hand and you just a lump of clay. Clay is a cohesive soil. There are two distinct categories of soil. So, anyway, what I was talking about is the gravity structures should be located on soil which has good bearing capacity. Especially say example is rocks or rocky bottom. Now, these type of structures normally come under the category of gravity platforms. Say gravity platforms, they fall under this category of foundation. They are called well foundations. So, in civil engineering they call this as a well foundation. The other one that I have talked about is the pile foundation. So, those are called deep foundations. a pile foundation is normally called a deep foundation. So, well foundations are normally come under the category of shallow foundations. Another type of foundation that you will come across is called a raft foundation, which of course we are not discussing because we are discussing gravity platforms. Now, gravity platforms they come under this category of well foundations, and here actually they have to be located on a particularly a rock strata which has good bearing strength. Now, another characteristics is that seabed should be flat. That is horizontal, because you are locating so much of weight, you cannot do this on an incline. Flat and horizontal, good bearing capacity. So, that is what you have to do. Now, these structures are normally, I will give you the diagrams, they have large amount of weight located at the base of the platform. So, your base is made particularly wide and heavy. So, these type of platforms are characterized by heavy and broad base. So, that means CG, you bring down this CG as close to seabed, as close as possible to seabed. That is why these structures you will find the base to be of say 2 to 5 meters deep, and this is grouted with concrete. So, this is concrete base. Now, on the periphery of this base, the steel plates are attached. So, you have large steel plates. So, these are called skirt plates. With dowels. So, like your pies that I have drawn, they are having teeth. So, here you have also sharp edges, these are called dowels. So, these actually go below your soil, or they are able to pierce the rock. Now, here after the gravity structure is able to sit on the seabed, located on the seabed, a portion of the structure goes below by means of its weight below the seabed, and these skirt plates actually are instrumental in cutting the rocks and taking the structure down. Now, here you will find lot of soil, but there will be gaps. So, these parts are void spaces, these parts you grout with concrete after you locate this structure. The reason is you have to distribute this load evenly on the base, otherwise what is happen, you get point loads coming from these undulations in the soil, and they are likely to rupture your base. So you grout the whole dam, this thing, base with concrete, especially you fill your voids. Now sometimes this is not possible, so you have to remove this soil by what is called a jetting facility. Jetting facility at skirt edge. So these are normally done. Anyway, so this is part of the structure. The other part that is important is that you make your columns, or this is cells, they call it cells. So this is actually a cellular structure. This is a monolithic cellular structure. And this is called dome. So this is the first thing that is to be built in the shipyard. Now next you start building your columns from the cells. And then you put your deck, or this is called a deck substructure, the same as in your jacket platform. So this is your columns, and this is called your deck substructure. Substructure means below the actual deck. So this is how it is built. So the three main parts of the structure is, number one is this portion. And this portion is called caisson. Number one portion they call as caisson. The number two portion is called columns. The third one is your deck. So the structure actually consists mainly of these three parts: caisson, column, and decks, or you can write this is a deck substructure. The main structure consists of these three components. So this is one, the other part is two. This is the third one, and this one is three. Now after this, what you do is, this caisson that is built, this is called a well foundation. Caisson is the well foundation. Now this is made watertight. There are various types of well foundation you come across. You may have a open well foundation, but that is not used in gravity structures. So these are the watertight categories. That means caisson by itself, what? Caisson by itself will be able to float. Yeah, this is why we are making a closed caisson. So this is a well functional watertight will be able to float. Now say 2 to 4 caissons depending on the size of the platform, 2 to 4 caisson cells, or rather you write caisson cells can be converted to columns. So these columns you are able to see this, that is these columns are nothing but extension of the cells of the caissons. There is you don't have the dome, you just continue your construction. Now all this is done afloat construction. Columns are not built in the shipyard. You have to do what is called afloat construction. Shipyard construction will just part of the base, that's all. So can be converted to columns, and this by a process what is called slip forming. So columns are actually slip formed over the caisson cells. They you just keep on adding the walls of the column. So this is done. Normally this takes place. The point that is to be noted is this is your waves. So wave load is coming somewhere here. Now here you can see that is your main wave load is actually taken up by the columns, not by the caisson. So the bending load that is coming will be taken up by these columns, and not only this, and down below you have hydrostatic pressure. The hydrostatic pressure will be quite large because of that rho GH formula. H is quite large at the base of the caisson. So here these factors are to be noted, and columns are to take large amount of vertical loads, vertical bending and buckling loads. So these type of loads are going to come into columns. Now here actually the cells you can store oil. Cells normally used. Now here what you have to do is at the outside, down below at the seabed level, you have large amount of hydrostatic pressure coming onto the walls of the caisson. Now unless you balance the hydrostatic pressure, that means the sides of the column is going to cave in. So you have to do a lot of pressure balancing. Now pressure balancing only you can do either you fill this caisson with sand, or you can fill this with mud or with oil. That is the oil that you are taking out from the, there will be the conduct duct pipes which are going, this is called the well head, that will be going down onto the well down below. So cells normally are used for storage. Storage of liquid mud used in drilling. So when I talk about drilling, you will come across this liquid mud, oil, or even water. Basically to balance external hydrostatic pressure. So, these type of platforms normally you will find in the North Sea, but the whole point is the hydrostatic pressure balance, what you are going to do in the columns. Columns, if you want to resist, then you have to make walls very thick. So, column diameter can be as large as say 10 meters in diameter. Column diameter, say column diameter can be as high as 10 meters with 1 meter thick wall. That is the wall thickness, column wall thickness. Now, here coming back, the columns you do not store oil. Oil is not stored in columns, but these columns are mainly used for, columns can take conductor pipes. Columns can house conductor pipes. That is why you do not store anything out here. This is one function of the column. So, all your conductor pipes are actually protected from the sea, because they are led through these columns onto the top of the platform. This is one advantage you are getting over the jacket platform. Jacket platform, the conductor pipes are exposed. So, columns can house conductor pipes, then you can house pumps. So, there are a number of columns serving different purposes. One column can house your pipes and pumps, other columns can have assays. So, they serve as assays to pontoon caisson cells. So, assays has to be provided in this region. That means, persons should be able to go down from the deck of the column. So, this is one advantage you are getting over the jacket structure. So, a person can literally go down right to the bottom of the structure through ladders through these columns. So, he is able to assess what? Assess your caisson cells, or sometimes this is called wellhead. Now, those of you who are not interested, they can go. You give your attendance and don't disturb me. This I don't like. If you are not interested, you give your attendance, you can quit. So, access to caisson cells, or sometimes these are called wellhead. So, here, so this is one part. The other part is wellhead assembly can be your blowout preventer. Now, this blowout preventer assembly has to be serviced. Not interested in the class, you simply don't come. You give your attendance at the beginning and then don't come. You tell, sir, I am not interested, you take my attendance and go. I don't like all this talking and laughing and giggling, then you quit. So, this blowout preventer assembly, this has to be serviced. So, this is readily done. So, because this is the main advantage over your floating platform, the BOP stack you can locate on deck, but BOP stack also you can locate down below, since you can access BOP from these columns. BOP access is critical, because for safe operation of the platform. So, one, it is serving for the conduct or a conduit for your pipes, your access, and housing the pumps. So, the other, I think these are the two columns. The other columns are basically for support. So, columns actually basically provide support to deck. And this deck area actually determines column spacing, deck area, and this you have to decide, deck area and deck weight. So, these are the two governing factors you decide on column size and spacing. Caisson, depth of embedment. So, this is again what you have to calculate. What is going to be your depth of embedment of Caisson? So, this is calculated from the well foundation mechanics. So, this is your say Caisson and this is your seabed. So, you find out how much is going to be your friction force that is coming from the soil, and soil will also give you a lateral pressure like this. So, the larger the amount of embedment, the larger will be the reaction from the soil. So, Caisson depth embedment you calculate from soil reaction. Now, this has to be done, otherwise there will be the whole structure is going to topple and slide. The other part that you should remember is what is called scour depth. Now, in case of jacket platforms, this is not a major cause of worry, because your foundation is a pile foundation. So, you have larger depth of penetration, but in this case of shallow foundations, scouring of the platform or scouring of the soil is very crucial for stability of the structure. So, what happens is that the soil gets eroded, there is erosion of the soil at the foundation. Now, this depth, of course, if you calculate, that is the depth of the embedment, this is always down below scour level. So, that means your structure has to go down below scour level. So, this depth is called scour depth. So, depth of embedment is always below scour depth. So, this you have to find from the local soil erosion, how much is going to be your scouring. So, this is one particular thing that is to remember. Now, the other thing that is other part of the structure which is normally important, actually we will find there are three types of gravity platforms. You can see in the diagram I will show you. gravity structures, three types. First one is called the condeep, then you have the sea tank, the last one is called Doris. There are three types of gravity structures. Doris design. So the condeep and the sea tank are more or less the same. As you can see from this, the picture is a bit hazy. This is your condeep variety. Now here actually you will find number of circular cells. Now all these cells are attached one with the other. So this is one cell and they are locked in by means of this kind of locking mechanism. All these cells are tied down. So this is actually called a honeycomb construction. So the cellular construction or caisson is in the condeep category. Condeep basically has honeycomb cellular construction. Now this type of construction, actually where it is more convenient, you go for that honeycomb cellular construction. That means here the individual cells can be formed in the shipyard and then they are linked. Now here also you can see in this structure the base. So you can see the double line. So that is the base of the platform, and this the dome is given. So this is the cap or the dome on the caisson. So each individual cells are built and they are connected by means of a locking mechanism. So this is the essential of a condeep type of structure. Now here the other variety is called the sea tank design. Yeah. Now in the sea tank you don't have this honeycomb type of base. So the other type is called a sea tank. Now sea tank is normally constructed as a rectangular or a square base. Now in this diagram you can see the base is square. So you have 3, 4, 5 cells, 3 or 5 cells across, 5 cells on the other side. So obviously you have 5, 5, 25 cells. Now here this can be either square or rectangular as the case may be, but you can see the construction of the cells. Now cells are not cylindrical, that means only the outer portion is having the cylindrical curvature, but inside they are all built in one monolithic design. That means they are not individual cells. These are the walls which are common to the next cell. So this is called the condeep, or sorry, this is the sea tank design. And the dome, instead of having a curved dome, you can see that it is given some kind of a flattish nature. So this is easier to build. This sort of structure is easier to build, and the same columns you can slip form and take the deck on top.
Then will all the cells have domes?
All the
Cells without domes, like already.
Yeah, all the cells, because the cells normally they have to be closed. The top of the cells have to be closed because they will give buoyancy. I will tell you why it is done.
No, sir, is it necessary to get a dome? Because sir, if they are square in shape, then it will become structurally some.
No, the top has to be closed. So this is the top of the cells. You can see in this diagram, but this is not carved like your shell. So, these have some kind of a flattish top, but they essentially all the cells have to be closed, because this whole thing is a caisson, and caisson is used primarily from the naval architecture point of view. It has to give buoyancy, and number 2 is used as storage for oil and water. So, this is a what is called a closed caisson. This is a closed caisson, where you have wells which are also having open caisson, but that is not used in gravity structure. So, this is a closed caisson. All caisson is closed caisson, well foundation. You can see well foundation in IIT. If you go to this Kasai river where they take the water, you will find that at the bank of the river you go down, there will be a big kind of structure. Have you seen this? All the pipes are going down over there. So, that is called a well foundation, but unfortunately that well foundation on top there is no roof. So, that is called a open caisson. So, this is basically this is called a closed caisson. Now, so this is your sea tank design. So, here actually in the ad hoc design you can see the conductor pipes. You can see some pipes, there are literally a host of pipes going through these columns, but also he has taken pipes outside your columns, but emanating from the caissons. Anyway, so the last is your after the sea tank you come to the Doris design. So, these are actually the Norwegian designs, they come from the Norwegian term Doris. Now, the Doris design, this is your essentially a Doris design. Now, Doris design are marked by 2 breakwaters. You can see one breakwater at the sea surface. You can see lot of holes over there. So, these breakwaters, they are used for damping your waves. So, the breakwater is actually protecting your conductor pipes which are coming out from this central shaft. So, this breakwater, this is Doris design essentially has breakwater. Breakwater at mean sea level, MSL. There is another breakwater, if you notice, at the seabed. You can see another type of wall with lot of holes at the base of the structure. So, there are 2 breakwaters, one at the sea level and the other is at the seabed. But at the seabed, why they have given this? There is no waves. This type of breakwater is used for countering your wave action. But what about this? Now, here actually there will be flow due to current. So, it is going to dampen the speed of the current, or lot of mud water is going to flow in this region because of mud circulation and with the current. So, that has to be resisted. You can see smaller diaphragm walls, you can see the stepped walls, right. So, one stepped wall is out here, the another stepped wall is in the dash line, and in between the crevice they are taking your pipes. So, these pipes are coming from the wellhead. So, wellhead pipes, that is your marine riser or conductor pipes, are taken up not inside this huge base. So, you can see this base is actually capped on top, but on the sides they are taking all the pipes, and this is actually piercing your breakwater wall, going through a central shaft which is not shown here, and then they are taking this up to the deck. So, the Doris design is used also for storage. You have oil storage out here, but essentially this design is used where you have large wave impact loads. Here wave impact loads will not, the design is such, that means these columns are taking the majority of your wave impact, but wave impact you are somehow mitigating or somehow reducing by means of these breakwaters. So, the gravity platforms are used primarily, the three types normally used where the condip and the sea tank is used in less waves. Doris design you can use for more extensive waves, and these are the two basic things, but all these designs are remarkable from one point of view, from the base, size of base. So, size of base can be as high as 224 meters base size, or size or width of base. So, this can be as large as 224 meters. Now, platform height. So, platform height can be as high as 190 meters. So, base dimensions, I told you, bases are to be made particularly heavy and wide. So, base girth or base width is of the order of few hundred meters. So, that is why the mass of the platform or weight of the platform is a few lakh tons, which is taking care of your weight. Now, these platforms, now when you make this in a shipyard, now shipyard you cannot, normally these gravity structures, the whole structure is never built in a shipyard because of the large size. So, in shipyard what they do, in this figure, I have one diagram out here, you can see the shipyard construction. Now, shipyard construction is limited to the caisson only, shipyard construction. So, shipyard construction you can see they are building this. So, this is your caisson. So, they have built some kind of an embankment, they are keeping out the water, and this is your dry dock, but they have made only the bottom part. So, bottom part consists of only the base slab along with part of the caisson. You never build the whole caisson on the shipyard. So, what is done is, in the shipyard construction is, say this is this bed of the dock, and you build some mock-up columns. These are called mock-ups. In your shipyard training, I don't know whether you have seen any this kind of mock-ups. These are called mock-up columns. Now, on this you build your structure. So, the caisson part is going to come like this along with your skirt plate. First you make your base slab. Now, base slab can be as high as say 2 to 5 meters. So, it will come a solid base you have to construct on mock-ups. So, this is grouted with concrete. Now, what is the, you build part of the caisson out here. Now, these caissons at the top you will find this is open, it is not closed. You build like this in your shipyard. So, caisson part construction. Part construction, open top. Why it is like this? So, you can see in the shipyard they are not building the whole structure, only this part is made in the shipyard. Now, after this is made, then you remove your embankment and float out. The whole structure is floated out, as you can see here. So this is this part of the structure that is shown here. That means in a smaller diagram you can see this base slab, a part of the pontoons, but it still has this open caisson. Caisson is open. Now here actually you have to be pretty careful. Why? Because on the one hand you are having a traveling crane. So here you have to do your hydrostatic and stability calculations, and you will find that the whole structure is tilted. If you have a crane like this at one side, as is shown in the picture, then that will cause a heaving moment. Now here you have to calculate the minimum freeboard, and there is also going to be entrapped air. This is going to be another cause of concern. Entrapped air below base. This will cause free surface. So, problem, no? So this you do hydrostatics and stability calculation at this juncture. So this is the naval architect's job. This has to be found out. Now remember, this is just like a ship without a deck. So the stability is given by what? Stability is always given by enclosed volume. You are not having any enclosed volume, but still this portion that is going to contribute to buoyancy. So you calculate the minimum freeboard requirement. Calculate minimum freeboard. With heel and trim. So that is, this is your job. Follow. Now after this is done, you start building the structure. Now here what is the first thing that you do is that you are not having sufficient freeboard. So that is, you start the sides of the caisson is made more longer. This is, and then you cap it. The first thing that you do in afloat construction. So this is afloat construction, and now the caisson will be floating like this. So this is afloat. Now the next stages you can see out here. So that means he has already completed the caisson part, and he not only on top of the caisson 2 or 4 cells of the, he has already built the columns have already been built. Now after this you have built this. Now the columns at this end is open. So you ballast the whole structure, it goes down. You take the deck on 3 barges. The barges you cannot see out here. Deck is taken on 3 barges on top of these columns, and then it is deballasted, and then it comes onto this mode. Here you can do anchoring also. Now, but in the transit mode, now this is your towing mode. Now, towing mode, you shouldn't tow the structure in this mode, because you may have insufficient stability. Why? Because you are not having water plane area. Your water plane area contribution is only coming from columns. But here you have a larger water plane area. But another problem with this is your G has gone up. So this stage and this stage you always calculate stability, hydrostatics, and so this is your towing mode, and in the final when it comes to stack again deballast the whole structure till your caisson sits on the bottom. So this is how your gravity platform is built. So thank you. Next class we will start about hybrid platforms.